So the goals after this section is to be able to really think more detailed about reaction mechanisms, how things actually react at the molecular scale. And so you want to be able to distinguish net reactions from elementary reactions or individual steps that all add up to a net reaction, identify the molecularity of elementary reactions. We'll talk about what that even means. Be able to write a balanced chemical equation for a process given its reaction mechanism, and then be able to derive the rate law consistent with this given reaction mechanism. So we have a little bit of work to do to get through all of these goals. So in your chemical education thus far, in Chem 107 and Chem 108, we've thought a lot about balanced chemical reactions like this example, the decomposition of ozone to oxygen. And we've thought a lot about what it means intuitively. In this case, it just represents the ratios of reactants to those of the products. And we can think that, okay, well, generally speaking, for every 2 moles of ozone that react, we produce 3 moles of oxygen. And that is true, and we can use that to do stoichiometry, we can do lots of things with it. One thing it does not tell us is the exact way that these things react together. That's called the mechanism. It doesn't tell us anything about whether or not these 2 ozone molecules actually collide with each other, or does one actually decompose into other things first and then react with the other. It tells us nothing about that. And that's going to be the basis of what we're thinking about with reaction mechanisms in the next series of sections we talk about. So in this example, how ozone actually decomposes is, as I alluded, through a 2-step sequence of individual reactions, and we call these individual steps elementary reactions. And if we look at these two, they'll add up to the overall net reaction that we're used to dealing with, which is the balanced chemical equation. And so if we were to add everything up in this expression on the right side, or on the left side, we would have 2 of these ozones. This oxygen and this oxygen atom would cancel, and this would produce 3 of these oxygens. This is the net reaction, but to get the net reaction, in reality, what's happening at the molecular level is you first have this elementary step, and then you have this elementary step. And in order to figure out or elucidate that, we need to understand kinetics, and we need to think about the orders of these reactions, their relative rates, and then we can ultimately deduce those steps from the balanced reaction. Another key aspect here is that anything that shows up as a product in one of the elementary steps, but then is again used in a separate elementary step such that they cancel in the net balance reaction. In this case, oxygen atom does not appear in the full balanced net reaction. We call those species intermediates, and that's an important idea. It means it exists in theory as part of the overall reaction, but the net amount of it is never actually present, because the second that this thing gets created, it gets used up and destroyed, and so we never actually create any of it in a net sense. So I'm going to rewrite this expression just so that it's easier to see. We have our 2 elementary steps here in pink, and then we have the net overall reaction, which is the balanced reaction we're familiar with. So it's important to note that the elementary representations of a reaction are physical representations of the exact reaction that's occurring at the molecular level. So for instance, this first elementary step means that we have 1 molecule of ozone, and then that breaks apart into 2 new molecules, 1 of oxygen and 1 oxygen atom. That can only be said, that interpretation of a reaction can only be said if you know that it's an elementary reaction. It cannot be said about a balanced chemical reaction, which is what you've dealt with in chemistry up to this point. That's the net change, which again implies nothing about those elementary steps. There's nothing about the blue net reaction that we see here that we could intuit or somehow understand intuitively that it's actually a composite of these 2 individual elementary steps. When we're thinking about elementary steps, there's this important classification idea called molecularity. And that's the number of molecules that are on the reactant side of an elementary step, not of a net reaction. And so in the case of this first elementary step, we only have a single molecule, that's ozone here. So we would say the molecularity is 1. Another way to say that is it's unimolecular. What that really is saying is what we already intuitively understand, that for this initial step that involves a single molecule, a unimolecule. It does not require two objects to collide in space. In contrast, the second elementary step does, right? There's one molecule, two molecules. We would call this molecularity of 2 or bimolecular, which tells us that we actually have to have a physical collision in space of these two distinct species in order for this step to occur. In this class, in organic chemistry, which you talk a lot about unimolecular and bimolecular reactions, we don't really go into greater detail than more than bimolecular. Once you add in a third, then you have what's called a three-body problem, where you have to have three objects co-locate in space and time, and that becomes mathematically really cumbersome and not something that is easily discussed at this level, and so we won't talk about it. We'll really be concerning ourselves with these two ideas.